Good evening, all radio amateurs. This is Bob DeVance, K5CRX, and this is the McKinney Amateur Radio Club's, as it turns out, weekly Amateur Extra license prep class that we've been doing. We're moving right along, still got a ways to go, but we actually are doing quite well when you get right down to it. We're still working on circuits and resonance, which we started last week, so we'll pick up there where we left off and continue the discussion of the questions and then go through the questions. This actually probably is going to work well because we'll go through the rest of the explanations, then go through the questions. That'll make a good review. The information on this particular set of questions, I guess, at least to me anyway, is a little bit daunting. It's a little bit difficult in some ways. So dealing with resonance and all the different things, a lot of the facts and figures there that you can memorize quite easily. You don't really have to memorize a lot of math unless you just want to. But at any rate, I think this will be good for us to go back and do that bit of review as we go all the way through the questions, do just this very rapid fire go question and then answer and go right through the questions one more time. There's actually about 56 questions in this block. So you're going to get a couple of these questions on the test. You can pretty well count on that. So we'll try to do what we can to make it as easy for you as possible. If we have time remaining tonight on that, which I hope we will, but we may not. But if we do, then we'll go on to components. The next couple of sessions, components and digital logic, I think will go fairly quickly. I don't see us getting bogged down too much in that. It's pretty much just factual information that we'll be going through on that one. So I think those two will go pretty quickly. And the last couple of sessions, again, I think we'll speed up considerably, but there's not that many questions to begin with, and the subjects are not that difficult compared to some of the things that we've done. So all of that being said, I think we'll have a good time with it. I think we'll get through it all right, and we're going to have a whole bunch of new amateur extras after field day, and of course that's our objective right now. This is session number 7 out of the 10. 3 more to go, getting close. I think, as I said, I think we will be able to complete all of this without actually having to have a supplemental class, but we can do a supplemental class if we want to, maybe on a Saturday or another evening, if that works best for everybody, or maybe just a session to come together and ask questions, talk about things, and maybe clear up any fuzz that happens to be there. We can certainly do that if we want to. That'll be up to you and the class as to whether we do a makeup session or not. And of course, as we said, then the end goal is to get you through the test at field day, get you tested there, and get that new license nice and shiny for you after field day. So with that, it will start here in just a few minutes after everybody gets logged in. We'll start shortly. Hang on. Okay, we're ready to hit it again for tonight. This is session number 7. We have 3 more to go, as we were mentioning a little bit earlier when some of us were talking. I think we're going to be able to complete all our material in the remaining 3 weeks. However, if we do need a supplemental session, or you just want one, or want a review session, whatever, we can certainly do that too. I'm certainly open to any of those kind of things we might want to do. Again, the goal, of course, is to get you pumped up and ready to go for the test at field day at last weekend of June. And away we'll go with that one. So looking forward to that happening. And with that, I'm going to just jump right in, share my screen, and we'll get going here. We'll pick up where we left off last week. Excuse me. My goodness, that went down the wrong pipe. Anyway, going back to resonance and all that goes with that, we were going through the review first, going through the descriptions first. We'll finish that up. And then we'll actually go through the questions and answer the questions as they are on the test. And then, as you recall, that second format has the question, then it has the discussion following. We'll just skip right on through that unless you have a question about it, in which case we can stop. We've got the discussion material right there, and it's easy for us to talk about it if something comes up you need to talk about. So with that, let me share. Come on, share. Be nice. And we want that one. Come on, be nice. And we're going to slideshow from the current slide. Okay, everybody okay with that? Can somebody give me a yes or no?
Yes, sir. We're good.
All right. This was actually the last one that we covered last week, so we'll just do a quick once over for this one, and then we'll move on. You'll recall that we have the reciprocals of resistance, reactance, and impedance. and that's the things that are listed here. Conductance, the reciprocal of resistance, which means it's 1 divided by resistance. Reciprocal of reactance, which is susceptance. Reciprocal of impedance, which is admittance. Today, they're called out in Siemens as the measurement term. Used to be called Mohs, which is ohm spelled backward. But at any rate, Siemens is the current term. And we use the letter B as in Bravo to represent that when it's being written out. All right, then here we go again. By definition, in the resonance circuit, inductive reactance, capacitive reactance are equal. I'm not sure how many times we said that last week, but it's still true this week, and it will always be so. For this particular question, they're wanting to know in the parallel circuit whether the Q, the quality of the circuit, is resistance divided by X. In this case, since the inductive reactance and the capacitive reactance are equal, you can use either one. So it's just the resistance divided by either one of those capacitive reactances will give you the answer. That's how you would come up with that answer. Let's see. In resonance circuits, the voltages that circulate inside a resonance circuit can be very high, especially on a high Q circuit. Mobile antenna series circuits are considered high Q circuits. That's why they say don't touch an antenna. When somebody's transmitting, you'll be very likely to get an RF burn from that if you do, because the voltages are very high at the tip of the antenna. Half power bandwidth basically describes a circuit that's passing a certain signal of a certain width. And when it starts to drop off, i.e. it can't continue to pass that signal through, at the point where it has dropped off to 0.707 times the original signal, which is the 3 decimal point, that would be the upper limit. Likewise, the lower limit is the same thing as the frequency starts to go up initially when the gain starts to really come up. So half power bandwidth shows that little diagram there shows what it is. Now, as far as remembering the formulas and all that, I'd recommend you don't worry about it unless you just want to. There's only a couple of questions with that, and they'll be fairly easy just to memorize the answers for those. To find half power bandwidth, divide resonant frequency in kilohertz by the Q. 7,100 kilohertz divided by 150 is 47.33, which is the answer to the question that's there. Of course, you can run that through the calculator if you'd like. We're going megahertz to kilohertz here. I believe the question is entered as 3.7 megahertz, which is 3,700 kilohertz, divided by 118 again gives you 31.4, 31.36 rounds up to 31.4. You'll see that when we when we actually see the question. In an RC circuit, a resistor capacitor circuit, assuming there's no initial charge on the capacitor, it takes one time constant to charge the capacitor up to 63.2% of the final voltage that it's going to charge up to, which would be the supply voltage normally. That's considered the time that it takes to do that is called one time constant. So we can actually measure that. We can put a voltage across the capacitor, put an oscilloscope across it, and we can actually watch that voltage rise across the capacitor to the 63.2%. We can also calculate what that time constant is very handily, and we'll see that in a subsequent slide. And if you have the book, you have this in the book. This is just a chart showing basically the same thing. Key there, the right kind of in the middle, top middle, the change in the first time constant, we're going up to 63.2%. The second one is when it discharges down to 23.3%. It's considered discharged. And then you have the chart there that shows you how you can calculate those things. And this works both with inductors and with capacitors. An RC circuit with all the components in parallel. This is doing some interesting things. They're solving for the time constant and playing games with us at the same time. In the question, there are two resistors in parallel with two capacitors in parallel. You remember capacitors in parallel, the values add. Two equal resistors in parallel, the value cuts in half. So when we divide those things out or multiply those things out, we get 220 seconds as the time constant. And again, you'll see that in the question when it'll make a little more sense to you, I think. If you inspect an old wireless station, which probably most of us have, and you see some interesting plumbing. Anyway, RF current travels along the outside layer of the conductor. And then as the frequency goes up, it tends to go even more to the outside of the conductor, almost no current at all into the center of the conductor. That's why, as it mentioned in the beginning there, that some of the antenna plumbing, they actually used hollow copper tubing because there was nothing flowing in the center of it anyway, so why have it there? Just use the copper tubing and let the current flow on the outside of that conductor, which was a piece of copper pipe. But it works good. That's called skin effect. VHF circuit can look pretty ugly. Yeah, I guess it can it? Straight line between 2 points isn't always the prettiest, but for VHF circuit, it's the path that works the best. You want to keep lead lengths very short when we're working with VHF. That's what they're working up toward. Anytime a piece of wire is a significant fraction of a wavelength long, it can become an antenna. Short of that, it can be an unwelcome inductor. Just a little half-inch of wire can actually act like an inductor that you didn't intend for it to be. To reduce unwanted inductance, keep all the leads in a VHF circuit as short as possible. That's it in a nutshell. Keep the leads short for VHF and UHF. Transmission line, well, the form of run of coax or copper trace on a circuit board. We think about that. Usually we think of transmission line, we either think of ladder line or we think coax. But it can actually be a copper trace on a printed circuit board, especially in the microwave world. You can actually create an antenna on a 3 by 4 inch piece of circuit board there just by working that trace and making it into an antenna on that little piece of board in the microwave frequencies. At any rate, any of those will reduce or will produce some form of phase shift, a little bit of phase shift anyway. So for a given length of transmission line, phase shift will be greater than as the frequency increases. Keep the transmission lines short, whether they're literal transmission lines or PC traces. The key is to keep the line short, to keep the phase shift down. Inter-turn capacitance on an inductor. When we have a coil of wire, there is a small amount of capacitance between the turns of that particular coil, which is the inter-turn capacitance, as it's called. So even though we don't have a capacitor hooked to the circuit, there's still some capacitance there. One solution was to use the old universal winding form, in which it would wind the turns of the coil back and forth at right angles, so that didn't happen so much. But at any rate, you have to watch out for the capacitance that's inter-turn on a coil. This is in there. I don't know where it's referred to, if it is at all. The left-hand rule showing the direction of electron current flow in a conductor and the magnetic flux around that conductor as the current flows through it can be determined by holding the conductor, at least symbolically, as it shows in the picture. Iron core transformer. We're getting to something more practical now. If you take a transformer apart, you'll notice that the iron cores that the wire is wound upon is laminated. It's little thin slices of metal. It's laminated in order to break up the magnetic path of eddy currents. Now, the magnetic path is key there. We're not talking electrical currents. We're talking eddy currents. Magnetic paths, magnetic variances that would normally go through a larger piece of metal. But by using the lamination, it doesn't allow it to do that. So, and then it mentions powdered iron or ferrite cores. Take that to the extreme because they have millions of little domains in there when that happens, much more so even than with a transmitter. But iron core transformer is laminated to break up the path of the eddy currents. Ferrite materials have the highest permeability of any of the commonly used cores, giving high values of inductance for a small number of turns. They're very, very good at handling magnetism. That's what the permeability means. However, ferrites are highly temperature sensitive. They can saturate easily. Saturate means it's got as much magnetism as it can handle. More current will not produce more magnetism. Powdered iron, having only about 1/100th of the permeability of the highest permeability of ferrites, are much more temperature stable, however. So there's a place for everything is what it boils down to. Powdered iron is good for tuned circuits that need to be very stable, it said not to vary up and down with temperature fluctuations. You need more windings for the powdered iron core than the ferrite core, but it's worth the extra effort. You remember the previous one we said the thing about the where was that? I can't put my finger on it right now. But anyway, we get with the toroids there, we get a lot of resonance out of it with fewer turns than some other materials. Brass is an interesting thing going on. Brass has negative permeability. It can actually be used to reduce the inductor and inductance in an inductor, which is kind of unusual. Some of the old radio gear used to actually use brass slugs. Essentially, they would detune the inductor in order to get a match that they needed with those brass slugs. I don't see that so much today, but it has been that way in the past. Ferrous material of any kind will increase the permeability of an inductor. They're subject to saturation, which means you put more current in, you don't get any more magnetism out of it, no further increase in the magnetic field. Most of the time, saturation is not a good thing, but there are some circuits that do employ saturable reactors. Before the varactor diode, you may remember, is a special diode that you can control the capacitance that it has by putting a voltage across it. It's a variable capacitor type of thing. Before that was invented, saturable reactors were sometimes used to create an electrically tuned oscillator or frequency modulator, but saturable reactors is the key to that question. Any real-world component has some parasitic characteristics, that is, like the coil that has that parasitic capacitance between the turns. Electrolytic capacitors are made by winding thin aluminum foil strips around something in the center, with a piece of paper between the strips to separate them. But when you wind those things together, you're going to get some inductance from that capacitor. So that's one of the things that happens, especially with electrolytic capacitors, as it mentions in the middle there. They have a great deal of parasitic inductance because, again, all that aluminum foil is wound into a coil really inside the capacitor. RF bypass capacitors need to have a very low impedance to ground at the operating frequency. Parasitic inductance, now go back to the inductor, can make the capacitor look more like an inductor than a capacitor, entirely defeating its purpose. So, okay. Would be nice if everything were pure. How true it is, but it's not. That's not the case. An inductor always has some parasitic resistance as well. Has some DC resistance going through the wire. And of course, it also has the parasitic capacitance with it. Every capacitor has some parasitic inductance, and every inductor has some parasitic capacitance. They're going either way you want to go with it. Normally, resistance has no effect on resonant frequency of a component, determined only by the capacitance and the inductance, the inductive capacitance and the inductive reactance. In a circuit that has both capacitors and inductors, the reactive power, now we changed subjects a little bit here, talking about power, oscillate back and forth between magnetic and electric fields and is not dissipated. You'll recall that we talked about a parallel circuit where the capacitor charges up, then as it discharges, the current goes back into the circuit, builds up the magnetic field, and the inductor, which builds up its magnetic charge. And then when the current stops flowing, that magnetic field starts to collapse, which regenerates the current and recharges the capacitor. So it goes back and forth and back and forth. When all that's happening, however, no power is actually dissipated. That is to say, there's no measurable power that's being used in that particular circuit when it's just going back and forth. Remember Eli the Iceman. Gives the relationship between voltage and current in an inductor or a capacitor. In a complex circuit, the reactive or the wattless power always has a phase difference of 90 degrees, either leading or lagging, depending on whether it's inductive or capacitive. Reactive power doesn't do anyone much good, but it's necessary to know to determine the voltage and current ratings of the various components in the circuit, because those components do have to withstand the different voltages and currents that go through those circuits as they're going back and forth. Okay, a little question here. 100 ohms of inductive reactance in the coil will not be a factor in this problem, as a pure inductance will not consume power in this circuit. And they're telling you up to front that it is a, excuse me, we got John Cash coming in just a moment. Let me get him on there. Okay. A pure inductance will not consume power in the circuit. Ohm's law, P equals I square R, results in 1 times 1. Comes up to 100 watts. Again, you can remember the formulas and calculate it out if you want to, but you don't really need to. Remember, the 100 watts of power is being consumed. All the power is being consumed in the resistor. The reactance does not consume power. Different types of capacitors have different loss processes depending on construction and frequency. Film capacitors. Film capacitors are little capacitors that are like electrolytics in a sense, but instead of being wound circularly, they're more like flapjacks stacked on a plate. You'll have a layer of aluminum foil, a layer of film, a layer of aluminum foil, a layer of film, with a connector on the top, a connector on the bottom, and the whole capacitor may be 1/8 of an inch thick with that. But because of that, they have the skin effect, just like our transmission lines. So they're not good at the higher RF frequencies. And we're not going to worry about that one right now. Letters AC are found in the words reactive. You'll notice AC is the meaning. It means out of phase. That's one way to look at it. It indicates non-productive power produced in a circuit containing inductors and capacitors. Since the phase of the inductors will tend to cancel the out of phase power of the capacitors, the reactive power then is wattless. That is, it's not using power, it's not dissipating power like a light bulb would, or a resistor that has a voltage across it and current flowing through it would produce heat. You'll not see that with the reactive circuit. It's not converted to heat and dissipated. Energy being stored temporarily in a field, then returned back to the circuit. So the capacitor stores the energy, returns it to the circuit. The coil returns its energy back to the circuit, and it goes back and forth in that format. Okay, and this is just the one that kind of comes in from the left side of the world, I suppose. Connect your radio's red and black leads directly to your battery's positive and negative terminals using the shortest possible run. Putting a fuse, of course, next to the battery's positive pickup point. Most people recommend putting a fuse in the negative line too, at least on the vehicle anyway. I also recommend to install some ferrite chokes on the charging system's leads. So if you're getting noise from a charging system, this could be from a battery charger, this could be from a charge from the alternator. Put some ferrite chokes on the charging system's lead will tend to suppress the noise coming from that charging system for the battery. One way to reduce RF interference coming from the line of an electric motor is to install an AC inline filter in series with the motor leads. That's called a brute force filter. Put this filter in line and it knocks out some of the RFI that a motor running puts out. Keywords this question are core material property. The material that determines the inductance of a toroid is the permeability of the iron donut. That's a ferrite toroid that they're showing right there, several different sizes and shapes. And the permeability of that thing, how much magnetism it can process, is the core material property. Okay, reason to use ferrite cores rather than powdered iron cores is ferrite cores require fewer turns of wire to produce a given inductance. That's what I was looking for a while ago. I thought it was behind us, and I guess it's in front of us. Anyway, ferrite cores require fewer turns to give a good inductance value. A toroidal core inductor, that's those cores we were just looking at, concentrates the magnetic field within the core material itself, protecting other nearby components from stray magnetic fields. The difference here, and you'll see this in a subsequent question, the difference would be what is called a solenoid coil, in which the coil is wound around an iron center bar of some kind of metal in the middle. When you have that type of a solenoid type coil, that magnetism will tend to go out and affect anything that's around it that can be affected by magnetism. Whereas the toroidal core tends to retain the magnetism within itself and not bother other things that are around it with stray magnetic fields. Okay, we're at the spot we want to be with that one. We're going to change to the other slide system here. All right, let me, any questions on anything before we switch to the other presentation? Okay, as before, let me get this one going here. Okay, are we okay? Everybody, somebody tell me if you're seeing that okay?
We're good.
Okay, here we go. As we said earlier, and each time as we go through these things, excuse me, we're going to You just got to go through the questions without a lot of commentary. But if we need to talk about it, that has the description following each question, we can certainly stop and do that. So if you need to talk about or want to talk about a question, let me know. Here we go. What can cause the voltage across reactances in a series resistive, inductive, capacitive circuit to be higher than the voltage applied to the entire circuit? At what point does that happen? Well, there's a term we call that when the inductive reactance equals the capacitive reactance, and that's when those are at the highest. What is that term? It is resonance. Okay. And explain it. Resonant frequency of a resistor, inductor, capacitor circuit, if R is 22 ohms, L is 50 microhenries, C is 40 picofarads. The best thing to do on that one is just to remember the answer to the next slide. 3.56 megahertz is the answer. And this is the, it tells you how to calculate it and so forth. Now, if you want to calculate it, certainly you can, but I would recommend just remember the 3.56. Fortunately, there are about 3 of these questions. There are not a lot of them. That helps. Resonant frequency, same type of question, different values. R is 33 ohms, L 50 microhenries, C is 10 picofarads. By the way, if you do calculate some of these things out, watch out for the micros and the picos, and keep your exponents in check so that you know where you are. And this one is 7.12 megahertz is the resonant frequency for that. And again, there's a formula for that where you can multiply that thing out. But again, probably if you just remember 7.12 megahertz, you would be ahead of the game. That's my suggestion. What is the magnitude of the impedance of a series resistor, inductor, capacitor circuit at resonance? The magnitude of the impedance of a series circuit at resonance. Think about that for a second. Okay, resonance here is the key. The circuit at resonance, the capacitive reactance, the inductive reactance are canceling each other and for all practical purposes don't exist. So the real magnitude of the impedance that's left is whatever the circuit resistance is. If it's a resistor, the resistance of the wire or something like that. But what only real resistance is left, or the impedance in this case is left, is going to be the actual resistance. The magnitude of the impedance of a parallel RLC circuit at resonance. Again, watch out for the resonance because it's still at resonance. That part didn't change. It's approximately, pardon me, equal to the circuit resistance. Again, the inductive reactance, capacitive reactance cancel each other out. Result of increasing the Q of an impedance matching circuit. Okay, Q is often used to describe tuning circuits. The better the Q, the narrower the band is that we're tuning into, the better we can pull out one single station. So as Q goes up, bandwidth goes down. We have a smaller or narrower bandwidth as the quality of the circuit goes up. The sharpness of tuning is the way they describe it here. Greater the Q, lower the bandwidth. Magnitude of a circulating current within the components of a parallel inductive capacitive circuit at resonance. Here we are again at resonance, which means that current is going from one component to the other, going back and forth, and it will be at maximum when it is at resonance. The two components will feed off of each other, basically. What is the magnitude of the current at the input of a parallel RLC circuit at resonance? Well, all of the stuff that's going on is inside the RLC circuit at resonance. It's almost as if it weren't there. So we'll have minimum input to it to keep everything going. We know it doesn't take much to drive it. It's almost self-driving, if you please. Phase relationship between the current through the voltage across a series resonance circuit at resonance. Now, again, watch out for that word resonance. If we're at resonance, that means the inductive reactance, capacitive reactance are canceled out. So normally where we would have a 90-degree lead or lag, we're not going to have either one here because it's at resonance. They've canceled each other out, in which case the voltage and current are in phase in a resonance circuit. What is the phase angle between the voltage across the current through a series resistor, inductor, capacitor circuit? If capacitive reactance 500 ohms, resistance 1K ohm, and inductive reactance 250 ohms. And again, there's some ways of calculating that, which you can do if you want. It's probably easier just to remember the 14 degrees voltage lagging. You remember we talked last time about the leading and the lagging using the little Eli the Iceman. So we say Eli, voltage leads current in an inductive circuit, which means current lags voltage in an inductive circuit. So sometimes you have to watch out. They get a little tricky in their leading and their lagging. But in this case, 14 degrees lagging is the one we're looking for. And again, you can do the tan, theta, and angles and all that good stuff if you want to do that, but you probably don't really need to do that. Same kind of problem. This time though the phase angle between the voltage across and the current through a series RLC circuit. Capacitive, I didn't fix that C there, did I? Capacitive reactance 300 ohms, resistance 100 ohms, inductive reactance 100 ohms, and again, it's easy probably just to remember that. And remember the leading, lagging again, 63 degrees lagging. And there's the figuring it out if you need or want to go through all that. You know, that alt 10 thing there at the bottom, or 10 to the minus 1 hour tangent of a number gets a little bit interesting. Phase angle between the voltage across current through an RL circuit, capacitive reactance 25, resistance 100, inductive reactance 75 ohms. Same kind of question, just different component values. 27 degrees leading. Relationship between AC current through a capacitor and the voltage across a capacitor. You remember we have voltage and current across the capacitor. Current leads voltage by 90 degrees. That's the ICE. Current leads voltage from Eli the Iceman. Relationship between the AC current through an inductor and the voltage across the inductor. And this is Eli. So voltage leads current by 90 degrees. Eli. What type of y-axis scale is most often used for graphs of circuit frequency response? This could be a little tricky maybe if you don't think about it, but we're going to do a little jumping forward here. The x-axis is normally always going to be the resistance value. The y-axis almost will always be the impedance values. The impedance values can get very large sometimes, and so in order to handle large values without having to draw a line a half a mile long, we use a logarithmic scale instead. So that's the key they're looking for there. The y-axis scale is often logarithmic. You remember logarithmic is where we can represent large values in a short space. Using rectangular coordinates to graph the impedance of a circuit, what do the axes represent? Well, I think I just said that the X represents the resistance, Y represents the reactance, and I don't think that's exactly, well, let's see, that's what they want. Axis, I think that's the right one. Yep. That one can be a little tricky, I think. X is the resistive, Y is the reactive component. You remember too on the Y-axis, inductance is always positive or going upward. Capacitance is always negative going downward on the y-axis. Which of the following represents pure capacitive reactance of 100 ohms in a rectangular notation like we were just talking about? Okay, now here's where we get into the J operator a little bit. The first value given in each one of those answers, the 0 or the 100, is the resistive value. The value of a resistance. The J tells us that what follows it is going to be reactance. The sign of the J tells us if it's capacitive or inductive. Minus J is capacitive, plus J is inductive. Okay, so this said it's pure capacitive, so it has to be minus. And the reactance is 100 ohms, so the only answer that fits is there's 0 ohms because there's nothing mentioned with that. It's pure reactance. The minus J says it's capacitive, and it has 100 ohms of reactance, so A is the answer. What kind of diagram is used to show phase relationship between impedances at a given frequency? Now, this is can be a little bit different thing. Using a phasor diagram, the phasor is one where we get into the angles more so than in the rectangular coordinates. We draw a line from the center of the graph outward. The length of that line represents the magnitude of the signal we're talking about, and the angle between the x-axis and the line itself is the phase angle of that particular reactive circuit. Phasor diagram. Think Star Trek if that helps. You bet. Where is the impedance of a pure resistance plotted on rectangular coordinates? It's always on the horizontal axis, the x-axis. What does the impedance 50 minus J25 represent? Well, okay, this is kind of like the first one we had, but here we actually have some resistance of 50 ohms. So we have 50 ohms of resistance. So there are two answers that fit that, A and B. The minus J tells us it's capacitive, and it's 25 ohms capacitive reactance. So we got 50 ohms and 25 ohms. Capacitive is answer B. That's the only one it can be. Can't be A because it says the minus says it's capacitive. Called the J operator. We could get into that a little more if we wanted to, and why we use the J operator, and why we use imaginary numbers, as they're called. But we're going to try to avoid that if we can. That's not on the test, so we'll try to avoid that for now. Okay, just a picture of what we've been talking about. In this particular figure, what best represents the impedance of a series circuit having 400 ohms of resistor, 38 picofarads at, and I've got to move something, give me just a second, at 14 megahertz. So again, we're going to have to do some calculations to get that out, but you can really, this is one of those probably easiest just to remember the answer. First of all, the 400 ohm resistor is easy enough. Remember, that's going to be on the x-axis. So if we go from the center point to the 0 point, right in the middle of that graph, and go to the right to plus x and go out to 400, we find there's 3 points. It can be 0.2, 0.6, or 0.4. So we know it's going to be one of those. Okay. We also know it's a 38 picofarad capacitor, so that says it's going to be a negative on the y-axis. It's going to be going down. And the only point there that matches that is 0.4. Which just by elimination, we come up with the correct answer for that one. That one's easier enough. But you can also calculate the different values as it shows all the different multiplications and things that you can do if you prefer to do that. Probably simpler just to try to remember 0.4. Okay, put a few more goodies in it and try it again. Which dot represents the impedance of a series circuit, 300 ohm resistor, 18 microhenry inductor. So that tells us, first of all, 300 ohms. We're going to go to the right on the x-axis to the 300 ohm point. That's right below 0.8. And we know it's an inductor, so it's going to be going up, not down. But here we got 0.3 and 0.8. So which one is it going to be? So we can't do a process of elimination on this one. We're actually going to have to remember which one it is. It's going to be 0.3, which probably makes more sense because you know that with an 18 microhenry inductor, it's going to have some pretty good value of impedance at that frequency. Again, you can calculate those things out if you need to and know exactly where it is. It's probably easier just to remember the 0.3 answer. And another one. Impedance of a series circuit, 300 ohm resistor, 19 picofarad at 21.2. Now here we go again, 300 ohms. We go out to the right, 300 ohms. We got 0.1, 0.8, 0.3. Picofarad capacitor, which means it's going negative, it's going to go down. So that leaves us with 0.1, doesn't it? On that particular thing, so we can do process of elimination on that one, which is fairly simple to do. Or you can calculate it and verify it if you really want to do that. What coordinates, excuse me, pardon me. Excuse me. What coordinate system is often used to display phase angle of a circuit containing resistance, inductance, and capacitive reactance? And that is polar coordinates, as they're called. And that's the one we talked about. Second, we talked about the rectangular. The polar is the one where we start out from the center of the graph. The line length represents the magnitude of the signal. The angle between that line and the x-axis represents the phase angle, called polar coordinates. How are impedance described in polar coordinates? This is kind of interesting. Magnitude and phase angle. The length of the line gives the magnitude. The phase angle is from the x-axis up to where the magnitude line runs out from it, from the center, which represents a pure inductive reactance in polar coordinates. Now, this one is a little bit different from the rectangular coordinates that we're looking at here. Okay, pure inductive. So let's see what we can come up with. Positive 90-degree phase angle. First of all, it's pure inductive, no resistance or capacitance to worry about, which tells us it's going to be 90 degrees already. Pure inductance, 90 degrees. Inductance always goes up, and capacitance goes down. So 90 degrees, of course, is the answer they're actually looking for. If we were plotting that, it would fall right on the y-axis going upward. Admittance, this is where we play with the terms a little bit. Excuse me. Boy, can't talk tonight. Admittance is the inverse of impedance, that is, impedance 1 over impedance. And these are, unfortunately, I don't know an easy way to remember those other than just brute force and remember it. How is impedance in a polar form converted to an equivalent admittance? So then we get into some really crazy technical stuff here. The reciprocal of the magnitude, take the reciprocal of magnitude, change the sign. And this is one you just have to, again, you just kind of have to remember that one, I believe. There's some reasons behind it, but I think just try memorizing the answer is going to be the right one. What is I can't even say susceptance. Imaginary part of admittance. Imaginary meaning that it's part of the resonance circuit that's not consuming power. That's why it's imaginary. Represented by the symbol, letter B as in Bravo. Okay. Effect of the magnitude of pure reactance when it's converted to susceptance. So we're going back in the opposite direction here, playing with these things. It's replaced by the reciprocal. Just to take its reciprocal. And again, I don't know an easy way to remember that, but just to remember it, brute force. How is the quality or the Q of an RLC parallel resonance circuit calculated? Okay, how do we calculate the Q? Resistance divided by reactance. Now, watch out for the word resonant here. Notice that, resonant circuit. Because it's a resonant circuit, the inductance and the capacitance are equal. So resistance can be divided by either one of those because they're the same value. So if we have inductive reactance of 50 ohms, capacitive reactance of 50 ohms, 50 ohms is 50 ohms. And if you had a 50 ohm resistor, it'd be 50 over 50, or you'd have a Q of 1 in that case. Resistance over inductance in this case. What is the effect of increasing Q in a series resonant circuit? Let's see here. Internal voltages increase. In fact, the quality of the circuit makes it more efficient. Voltages increase. I guess that makes sense, doesn't it? You have some very high voltages there, again, like the mobile antenna whip that we don't want to touch when somebody's transmitting. The half power bandwidth of a resonant circuit, a resonant frequency of 7.1 meg, and a quality of 150. And again, there's a formula to do that, but it's probably easiest just to remember that it's 47.3 kilohertz. Kilohertz. That's the only 47.3 that's out there. I'm not sure if there's an easy way to connect that to something, but again, probably just try to remember. You know, you can do the division if you remember how to do the division. And I didn't fix this. It's supposed to be 7,100 divided by 150, not plus 150 there. I fixed that on another set of slides. I didn't fix it on this one. I missed it. Half power bandwidth of a resonant circuit has a resonant frequency of 3.7, a Q of 118, 31.4. Fortunately, that's the only one that's there. If you can relate the 31.4 to the 3.7, that might help. It help you remember it. I don't know if it will or not. Again, you can calculate it. Again, that should be a division, not a plus sign there, to give us 31.36 rounded to 31.4. Term for the time required for a capacitor and RC circuit to be charged up to 63.2% of the applied voltage or to discharge back down to 36.8 of its initial voltage is called a time constant, one-time constant. Fortunately, you don't have to calculate that. That's just a given. What's the time constant of a circuit with two? This is one we talked about earlier. Two 220 microfarad capacitors and two 1 megohm resistors, all in parallel. Okay, so we got two 220 microfarads in parallel, two capacitors with the same value in parallel merely add, so we got 440 microfarads. Two 1 megohm resistors in parallel, two equal value resistors in parallel, half. So that would be a half of a half a megohm for that sort of thing. So the half megohm times the 440 comes out to be 220 seconds. And you can calculate that out if you want to do that, but that's the essence of it. Fortunately, this is one of those where we got the megs and the micros, the exponents are the same. We're taking microfarads and megohms here, as opposed to picofarads, for example, in which case we'd have to watch out for the decimal points. We don't have to do that here. Result of a conductor skin effect. Remember, that's where the RF current flows out on the very surface of the conductor. Resistance will increase because the current goes out close to that surface. There's less surface on which it will flow. So the resistance actually increases as the RF frequency increases. Why is it important to keep lead lengths short for components? We want to minimize anything that's inductive by using as short leads as possible. Leads have inductance. Why are short connections used at Why are they used at microwave frequencies? And again, reduce phase shift along the connection, because you can get phase shift if you have some long connections with inductance involved, and it would introduce phase shifts, keep everything short. Parasitic characteristic creates an inductor self-resonance. Now, we can take a coil, and if it's the right values, et cetera, apply an AC signal to it, and the coil itself can become resonant with its own self-capacitance that it has built in between the turns. That can't talk tonight. Parasitic characteristic of the whole thing. So let's see. What parasitic characteristic creates inductor self-resonance? The interturn capacitance, that is the capacitance between the turns of the coil. Why are cores of inductors and transformers sometimes constructed of thin layers? You remember the eddy currents? We want to get rid of the eddy currents. Excess magnetic fields flowing all over the place, out of control. Which of the following materials has the highest temperature stability of its magnetic characteristics? That was the powdered iron, you'll recall, because all the little tiny parts of the powder there are like individual magnetic domains. And so we don't have any chance for eddy currents to flow with those, and it makes it temperature stable. Which type of core material decreases inductance when inserted into a coil? You remember we talked about the broadcast transmitters using brass inserts to detune their coils. And so the answer to that, from that, you'd probably, whoops, I'm sorry, excuse me. Sorry. Powdered iron, we did that one. There we go, brass. Sorry, I hit the wrong button. What causes inductor saturation? It's the point at which you can't put any more current into it to change the magnetic field that's coming out of the thing. Operation at excessive magnetic flux. So that means the magnetic flux is as big as it's going to get. It's not going to get any bigger, even if you put more current through it. It's inductor saturation. Operation at excessive magnetic flux. It's doing all it can. What parasitic characteristic causes electrolytic capacitors to be unstable at RF? Is the inductance that's built in because of all those turns of aluminum foil that are coiled up inside that electrolytic. What combines to create the self-resonance of a component? Components, nominal and parasitic reactants. Those little things that it picks up, like in the electrolytic capacitor, picks up inductance. We mentioned the film capacitors picked up some inductance. The inductors picked up some capacitance between their turns. Parasitic reactants, in that case, it's nominal parasitic reactance determines the self-resonance. What happens to reactive power in ideal inductors and capacitors. Now, of course, there's no such thing, but in a theoretically ideal one, reactive power is just there. It doesn't do anything. So it's there, it's stored in a magnetic field in the coil and an electric field in the capacitor, but it doesn't consume power. It's not actually doing any work per se. It doesn't produce heat. The phasor relationship between current and voltage for reactive power, 90 degrees out of phase, just like anything else. We have a current voltage and a reactance. The reactance is going to cause the current voltage to be 90 degrees out. Whether it's going to be leading or lagging will be determined on which is the greater value, X sub C or X sub L. How much real power is consumed in a circuit consisting of a 100 ohm resistor series with a 100 ohm inductive reactance drawing 1 ampere? That's a mouthful, isn't it? Okay, 100 ohm inductive reactance drawing 1 amp. What do you think it's going to be? Would you believe it's just 100 watts? We just calculate that with just the resistors, all we have to calculate, because the inductive reactance doesn't do anything for us. 100 watts is the answer. Primary cause of loss in film capacitors at RF, the skin effect, that is those outer edges of the top and the bottom of it. The RF will tend to go to those little layers that's on the outsides of the capacitor. Reactive power. Okay. It's not power consumed. We've said that already. It's not something that we can really use. It doesn't have anything really to do with QR resistance. It's wattless, non-productive power. We have to be aware of it because there are currents and voltages involved. We have to know the power, the theoretical wattless, non-productive power rating in order to rate our components so that they will withstand the currents and voltages that are involved in a resonant circuit. How can conductive noise from automobile battery charging system be suppressed? Remember, that's where we put the filters on it, using ferrite chokes as a filter. Put ferrite chokes on the charging system's lead. This would be on the alternator output lead. If you can get to that, some of the vehicles these days, you can't even get to that. But if you can get to it, you put a couple of ferrite chokes, clamp on ferrite chokes will help reduce noise in the charging system. Or if it's getting noise from a charger that's plugged into AC, the same thing would apply. Put ferrite chokes on the leads that go to the battery. What's used to suppress RF interference? A line-driven AC motor. You want brute force with that thing. Just overpower it with filtering action. What core material property determines the inductance of an inductor? That's the permeability of it. I don't know if there's any easy way to remember that or not. How do ferrite and powdered iron compare for use in an inductor core? Ferrite cores will take fewer turns, you will remember, than the powdered iron. What is the primary advantage of using a toroid coil instead of a solenoid core in an inductor? Remember, the toroid is using that little donut-shaped core with white turns around it versus a solenoid core, which is a piece of metal with wire wrapped around it, just a straight piece of metal. Okay. The toroidal cores confine the magnetic field within their own core material, whereas the solenoid core will splatter the magnetic field all over the place. Would you believe that's the end of that slide pack? Wow, we did it, gang. And how are we doing here overall? 7:55. We are doing good, aren't we? Anybody have any comments, questions, or thoughts here? We've got about 5 minutes, so what do you think?
It wasn't too bad.
Sometimes it still feels like we're drinking from a fire hose, I suppose.
Yes.
But tell you what, let's do. We've got 5 minutes. Let's not waste it. Let me bring up the next one on this. Let's see. We want to do components. Presence is 10. Components is 11. That's the one. Yep. 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 And let me go back to me and share. Okay, do we see that one okay?
Yes.
All right. I decided on this one, we would just go straight through the questions. I didn't feel like we needed to go through the explanations first and then go back through the questions. So we'll just kind of introduce this one, talk about all the different kind of components that's in the rig. This is a fairly, I don't remember how many questions is in this set, but it's not real long nonetheless. So that'll give us a little bit to go with. So here we go. What application is gallium arsenide used as a semiconductor material? Now, we'll be talking a lot about semiconductors. That'll be diodes and transistors of various types. The gallium arsenide is the material used in it, or it may be a doping material, as it's called, if it's added to silicone or some other kind of material. And unfortunately, these are just things that you just have to remember. I don't know an easy way to say that. Gallium arsenide, microwave. Okay, you mentioned FETs, GAAS FET is gallium arsenide, FET, field effect transistor. Transistor has excellent gain, very low noise figure, which is why it can be used easily in, well, I said it doesn't mention they'd be used in microwave circuits. Which of the following semiconductor materials contains excess-free electrons? Now, you remember in the semiconductor, electrons break free and go into holes and go from a negative material into the holes of a positive material. So what the following materials contain free electrons? It's going to be the negative or the N-type material, negative electrons. Okay, name given to an impurity atom that adds holes to a semiconductor crystal structure. So on the P side, we want to create additional holes for those electrons to go into, if you please. So what's the name given to that? It's going to be an acceptor impurity. It's going to make that material accept more electrons. If that'll help you to remember that just a little bit. How does DC input impedance on the gate of a field effect transistor compare with a bipolar transistor? You remember the field effect transistor has gate, source, and drain, where a bipolar transistor has base, collector, and emitter. They both do essentially the same thing, but their characteristics are much different. One of the big differences is the way the field effect transistor is made. Its gate, where the input signal comes in, is isolated from the rest of the internal circuitry of that FET by a very thin layer, which gives it a very, very high impedance. So the FET has a very high input impedance. Okay, let's grab a couple more and then we'll let it go for tonight. What is the beta of a bipolar junction transistor? This kind of gets into some old stuff here. Change in collector current with respect to the change in base current. And unfortunately, you just have to remember that beta goes with the old junction transistors. If that helps a little bit, you might put that in the back of your mind to remember that. Next time, we'll probably just start at the beginning and come right back through these again. Beta, there is an alpha. There it is. The alpha of a transistor was deemed to be more basic. Let me see, did I say that right? Yeah. Beta, the bipolar, alpha was the older standard for old transistors. Sorry, I didn't say that right. Which of the following indicates that a silicon NPN junction transistor is biased on? NPN means negative, positive, negative. And what do we measure in order to find that out? We measure from base to emitter, which is just like measuring across a diode. A silicon diode has a forward voltage drop of 0.6 to 0.7 volts. The base to emitter is essentially a diode inside that transistor, really, in a regular junction transistor. So we measure base to emitter voltage at 0.6 to 0.7 volts. That would let us know that the transistor is turned on. If the voltage is less than that, the transistor would be turned off. What is the term of the frequency at which the grounded base current gain of a bipolar junction transistor is decreased to 0.7 of the gain obtainable at 1 kilohertz? And that's just one of those crazy things called the alpha cutoff frequency. And I don't know an easy way to remember that one either. It's there. Grounded base, common base means the same thing. Common base means alpha. Okay, we'll make this one our last one. What is a depletion mode field effect transistor? What is a depletion mode? Might be the first question to ask. The depletion mode is a region in which there are no electrons flowing, basically. That's essentially what it boils down to, or very few electrons are flowing in that depletion mode. So a depletion mode field effect, nonetheless, has a small current flow between its source and drain anyway, even if there's no gate voltage applied to it. Normally, the gate voltage would control how much current flows through the FET. But the depletion mode type, there'd be nothing at all on the gate, and it will still conduct a small amount of current, not a lot, but a small amount nonetheless. And that's probably a good spot to stop right there. We're on E6A09. Okay, gang. Well, let's see. It is 8:02, so I like to try to stop on time. Anybody got any thoughts or comments or questions or otherwise? We'll try to field it.
Oh, work on it for another week.
Okay. I don't know about you guys, but this hour seems to me like it goes so quickly. It just seems like it's zipping, it's gone. You guys have to listen to me drone on and on. So, well. Don't have time to tell jokes. We got too much to cover. Okay. Any other parting comments? Any thoughts from anyone at all? We'll take that and then we'll shut her down for the night.